pretty sure that's right. For the concept test in the back. Where did we leave off on that? Nobody's going to tell me. We finished them? Okay. Is that true? Okay, good. All right. Well, we'll move on then to Chapter 6. Chapter 6 and 7 are induction and inductance. We're on the weekend. Yep. You don't have long left in the semester. You really just have, 2 days this week, and then when we get back, we only have a week and a half. And we'll have our last exam, that fourth exam, on the Monday of that last week. We meet Monday and Wednesday of that week, as I understand. That's correct, right? Wednesday's the last day of class. Yeah, so we'll have our exam on that Monday. I know that's different from last semester, but I thought that Wednesday we really need to have to get you guys ready for the final and sort of talk about the final and get your exam back to you and all that. So we'll have that exam on that Monday. Okay. So we're going to get into induction and inductance. That is how we use magnetic fields to generate electricity. And then we'll get into circuits that use inductors. And inductors are just a coil of wire. But they do some pretty funky things in circuits when we insert a coil of wire because of the magnetic fields that they generate and how that affects the flow of current in a wire. So we'll see that these LR circuits, that is with an inductor and a resistor, LC circuits, that's with an inductor and a capacitor, and we'll see how they interchange between the energy. And then finally we'll look at LRC circuits, where we'll see damped harmonic oscillators. So we'll see some different mathematical tools, like we'll get just a tiny little bit into first order differential equations, but nothing terribly complicated. Really, we're just going to sort of show a solution for a differential equation, and then see some of these different functions that come into play that you may not see LR, LC, or LRC circuits in the future, but you'll probably see these different types of functions. So I want you to know how to deal with those. So this first section is just on how induction works and some of the initial work. A current causes a magnetic field. Like we saw that before. That when we have a wire with a current going through it, that it generates a magnetic field. You know, we can find the direction of that magnetic field. We can find the magnitude, that was that mu naught I over 2 pi r. We know that a current creates a magnetic field. And then similarly, a current is caused by an electric field. That is, if I think of a wire, say this is my wire, the inside of my wire, I think of my charges, we'll call them electrons, they're moving along, or we'll call them protons actually, to sort of stand in the general idea of what current is. What's causing them move is that there is actually a electric field that's set up within the conductor. So we have this electric field that is causing these charges within the wire, we call them protons, but really they're electrons, to move within that wire. And so at its very basic level, a current is created by an electric field. And so Faraday came up with this law of induction, and he showed this experimentally that it could work, is that a magnetic field can induce or cause an electric field. A magnetic field can induce or cause an electric field, and hence a current. Now we've already talked about this, so this shouldn't be dramatic to you, right? Because we talked about how electric motors, they take an electric current and they go through a coil and they cause a thing to turn. Well, the reverse of that is true, that I can take a magnetic field and a coil of wire and apply a force to it, and then that generates an electric current. That's sort of what we're talking about here, that if I have a magnetic field that I can use it to induce a current, or I can use it to induce an electric field. And he did 2 experiments. And we'll do one of them here today, I'll show you. The first experiment is he took an ammeter, you know, sort of the late 1800s version of the ammeter, which was not that much different actually than the one we have today. And he hooked it up to a wire that looked something like this. So he had over here a coil of wire, and he took a magnet and he moved it back and forth within the wire. So he moved it into the coil and out of the coil. And he found that moving the magnet causes a current in the circuit. We used to do this experiment in the lab, but we got rid of it for various reasons. Let me show you. It's not that difficult. So this is a galvanometer. Y'all have used this in class. All right, so this is just a coil of wire. I'll pass it around and you can look at it. I had talked about this before. This is called magnet wire. This is the wire that they use in electric motors. It has a very thin insulator over it. So remember I showed you the video of the lady that made the lady or the guy, I don't remember, that made the armature, and they used wire that had a thick coating. I said you could use magnet wire. This actually is magnet wire too, but it just has a very thin insulator over it so that when you wrap it up into a coil like we have here, that you don't get currents jumping between wires, just so that they're insulated. Anyway, this is magnet wire. It's wrapped around a toilet paper roll, I don't know, about 50 tons or so. And I have it hooked up to a galvanometer. And what I'm going to do is I'll take a magnet, and this is very much what Faraday did, is I'll take a magnet and I'm going to pass it into and out of the coil of wire. So watch the galvanometer. I'm going to hold down the most sensitive button here so it can measure the current. So notice that every time I move the magnet through the coil of wire, I cause a current to act. And notice if I move it in one direction, it goes in one direction, and if I move it in the other direction, the galvanometer goes in the other direction. That just means that when I'm moving the magnet in one direction, it changes the current goes in one direction, and then when I withdraw the magnet, the current goes in the other direction. I also want you to notice something else. Let me try to get both of them in here. Let's see. So watch. Stick into the thing. So as I pull it out, and then when I put it in, now notice the magnet is inside the coil here, and there's no current. But that doesn't make sense because I said that a magnetic field will create a current. So what's the deal? I have a magnetic field around the wire. Why is it not generating a current? Why do I have no current when there's a magnet inside the coil of wire? Okay, yeah, sort of. Doing no work is not moving. Right, so the magnet has to be moving in order for the current to be generated. So watch, I put it in, it stops, there's no current. When I pull it out, it stops, then there's no current. In, out. And then also, if I do it more vigorously, I can get more current. So if I do it faster, I get more current that goes through the galvanometer. So really Faraday's law says not that a magnetic field generates a current or an electric field. I'm setting up an electric field inside this magnet wire. But really what it's saying is that a changing magnetic field will generate an electric field. A changing magnetic field generates an electric field. So let's sort of revise that idea. I'll pass around this. This is an inductor. It's a lot like a solenoid too, but we'll talk about this later in circuits. An inductor is this. An inductor is really just a piece of wire that's wrapped up in a coil. And we'll see that in the next section of this chapter, really in chapter 7. But this is what we call an inductor. Although they don't usually have it on a tissue paper roll. But it is an inductor. Okay, so current occurs. Couple ideas here. Current occurs when the loop or the magnet moves. I was just moving the magnet, but you could conceive that instead of moving the magnet, I could hold the magnet still and then just move the loop. And in fact, that's what you do in a generator, right? You don't usually move the magnet around, you move the loop around. Oh, that should be an in there. So current occurs when the loop or the magnet moves. The second thing I want you to notice is that you get a greater current when it moves quickly. A bigger current when it moves quickly, when the magnet moves quickly. If I move it more vigorously through the inductor, then it generates a bigger current. And then the third thing is that the direction of the current is dependent upon the motion of the magnet. All right, the direction of the current is dependent upon the motion of the magnet. We'll see all those things come up as we deal with Faraday's law. He did a second, thank you, Elaine. He did a second experiment, just similar to the first. We're not going to do it here, but I think that you can envision how it worked. That he had the ammeter set up. He had a coil of wire like this. So this is just a coil, kind of like our inductor. Just he had a loop of wire looped around a bunch of times. And then he had next to it another coil of wire. So these aren't touching, but I'm going to draw them close together because that's the way he did it. So he had two coils of wire that were sort of parallel to one another and not touching. And this was attached to a power supply. And so I think you can envision what's going to happen here is that when I turn on this power supply and I have a current that's traveling through this loop of wire, then that's going to generate a magnetic field. And then if I can change the power supply such that I'm modulating the current that comes out of here, then it will modulate the magnetic field. So I'll have a changing magnetic field here, and that's going to generate an electric field over here, because a changing magnetic field generates an electric field. So you get an induced current when you turn on the switch, or when you turn on the power supply. Let's see. An induced current when you turn on the power supply. And then if you can change the current here, it causes a changing magnetic field here. And then that induces a current or inducing an electric field, which is a current. An electric field causes a current here. All right, so this was a very similar experiment it was basically, instead of having a magnet that he moved through the inductor, instead of doing that, he made an electromagnet. And he made an electromagnet that he changed, modulated the magnetic field by changing the current. He turned the current on, he turned it off. He turned it on, he turned it off. And then that would cause a magnetic field to be induced by the blue loop, which would generate an electric field in the red loop, which is causing a current. An electric field causes a current. All right, and he came up with this law, Faraday's law. It's called the Faraday's law of induction. It says an EMF is induced. Remember EMF? That's our electromotive force, right? Is induced when the number of field lines, when the number of magnetic field lines that passes through the loop is changing. This is almost exactly what we said before, but before I said, I didn't say EMF, I said an electric field was induced, which causes a current, but it's the same idea, that an EMF causes a current, an electric field causes a current. In fact, an electric field, we can go back and thinking about our two parallel plates that are separated. We sort of had this cartoon model of an electric field between two plates. And we decided that these have this electric field because there is a difference in potential between those two plates, and that's why I get an electric field that's set up. So I'm sort of using EMF, electric field, and current all sort of interchangeably. They're all sort of causing one another. That the difference in potential creates this electric field, which causes charges to move between the two plates. Okay? You know, with me, sort of bringing together a lot of ideas here. With me so far? You excited to be here on Monday morning? Because you look excited. Are you? Okay, so let's go back and think about magnetic flux. We've seen this before, but you're going to see it again. In order to find the EMF, you have to be able to calculate the magnetic flux. And if you remember, our magnetic flux, or we've done different types of flux, but our magnetic flux, phi of B, is equal to the integral of B dot dA. Where dA is a vector perpendicular to the area. All right, we do a lot of fields in this course. Actually, I think at LSU they call this course just fields. That's all they call it. But anyway, dA is a vector perpendicular to the area. So remember, if we have an area, say if I have a little segment of area, I call this dA. It's a vector, or rather the vector dA is perpendicular. The vector dA is perpendicular to that surface. Yes, y'all remember? We had that chapter 0, chapter 1.5, and then we had it somewhere else, I forget. But we'll need to know how to calculate the flux again. So if the B field is perpendicular to the loop, then you get something that looks like this. You get, say this is our loop of wire right here. We have our magnetic field, say into or out of the page, so that it's perpendicular to that loop of wire. Then in this case, theta is equal to 0. Because we're looking at the area, sort of draw over this, my area vector is right here. This is dA. And my vector dA is perpendicular to this. So actually, my angle would not be 0 degrees. In this case, it would be 180 degrees, depending on how I look at my dA. But nonetheless, it doesn't really matter. We can assume that it's 0 degrees. Theta is equal to 0. So B dot dA is going to be equal to B dA cosine theta. Or since theta is equal to 0 and cosine of 0 is 1, it's just going to be B times dA. And then if I want to find phi, the magnetic flux is going to be the integral of B dot dA, which is going to be the integral of B dA. I'm just taking this and putting it in for that, which is just going to be the integral of B dA like that, assuming that B is constant with respect to our coordinates. I think that's going to be true most of the time, and it's just going to be B times A. So we've seen this before. We've seen it for electric field lines, we've seen it for gravitational field lines, and now also magnetic field lines. That our flux we can calculate as just the product of the magnetic field times the area through which it goes if it's perpendicular to that area. If it's not perpendicular to that area, we have to include a cosine theta term. But in this case, it is perpendicular. Phi my flux line is equal to, or the unit for this is the Tesla square meter. Because you get Teslas here, you get square meters here, and 1 Tesla square meter is equal to 1 Weber, which we abbreviate as 1 WB, 1 Weber. I don't know where that comes from, the Weber. There was a famous scientist, but it was like mid-20th century, so I don't think it's him. I'm not sure where it comes from. All right. So we haven't really said anything new so far. That we've seen different things sort of come together. But you've seen flux lines, you've seen field lines, you've seen calculating flux from the field, and we've also seen this idea that a changing magnetic field creates current. That's the idea behind a generator. But we're just starting to formalize this a little bit. Okay? Yes? All right. Let's look at Faraday's law, and we'll do some calculations and look at how we can apply it. It says that the EMF is equal to the rate. I've already said this, but just sort of a little bit differently. Is equal to the rate at which this flux changes. You know, that's the phi. It's the rate at which that changes. And then also, the EMF generally opposes the change of the magnetic flux. That's phi. We'll see this in a bit, but yeah, we'll just sort of, I'll leave it at that. We'll come back to it. We'll see that. But the EMF, where's my, I like to think of this as what's going on in the wire likes to balance out what's going on with the magnet. And so if I'm pulling out the magnet, it's like the wire is acting to hold the magnet in place. I'll bring a device next time that will demonstrate it a little better, but we'll see this when it comes up in our calculations. But as I pull out the magnet, it's like the wire wants to hold on to the magnet, it wants to keep the status quo, and so it will generate an EMF, which generates a magnetic field that will hold the wire in place. So for now, just keep this idea in your mind that the EMF is going to oppose any change in the magnetic field. Okay? That it's going to actually generate a magnetic field that will be opposite the magnetic field of this, which if it was strong enough would just keep the magnet in place. So if I try to pull it out, you'll feel resistance against pulling the magnet out. I have a device that shows that, and I'll bring it next time. I forgot to bring it today. But the magnetic field, the coil of wire will resist any change in the magnetic field. And that's why the EMF will oppose the change of the magnetic flux. And so we express this mathematically like this. We say that the EMF, that's that script E, is equal to the negative, that's because it opposes, the rate at which the flux changes. And so we express rates of change as what? If I tell you, goodness, bless you. I was thinking this morning that my students have been sneezing a lot, and I thought that it was because they were in Peltier Hall, but maybe it's just y'all are sneezy this time of the year. Lots of pollen in the air, right? Okay, I'm sorry. That was an aside. But what was I saying? Oh, rates of change. So when we talk about a rate of change, how do we usually express that? When we're talking about anything, say like a rate of change of position, how do we express that? A derivative, right. So we talk about a derivative with respect to time. So if we're talking about the rate of change of the magnetic flux, we say that it is the derivative of phi with respect to t. So this is sort of a new thing, that the EMF is equal to the negative, because the EMF opposes the change of the magnetic flux to the rate of change at which the flux changes, which is dp dt. And then if we have multiple turns of wire, then this just becomes E is equal to negative N d phi dt. All right, where I have N is just the number of turns of wire. We have three ways to change the flux. You ready for them? Yep. Three ways to change the flux with time. We can change the magnitude of the magnetic field within the coil. And this is what Faraday did. I'm going to redraw this figure where we had the two coils up next to one another. We had another coil here. That's what Faraday did. He changed the magnitude of the magnetic field within the coil because he would turn this on and turn it off. Turn it on, turn it off. And then when he did that, he would see that he would get a little jump in his ammeter needle, just like we did with this thing when I had moving the magnet in, moving it out. So that's one way to do it. There are a couple of other ways that are a little more practical and ways that we do this instead. You can change the area of the coil. Because we said that phi was equal to B dot dA. So we can change the magnitude of the magnetic field. We can change that. We can also change the area to change the flux with respect to time. What's something else that we can do? And this is the most common of all. And it's kind of hard to take your coil and change its area, make its area bigger, make its area smaller. What's the most common way to change the magnetic flux? It's not changing the magnitude of the magnetic field, although we'll see that with transformers that's sort of what we're doing. It's not by changing the area of the coil, just because that's not very practical to make your coil bigger, make it smaller, bigger, smaller. What's the most common way? And that's this third way. What's something else that we could change to change the magnetic flux? Now this is our expression for magnetic flux, E dot dA. I said I can change B, I said I can change A. What's another thing that I can change that would alter the magnetic flux, that would make this flux change? Think about it for a second. It's not written up there, but it's implied in that expression of B dot dA. I can change my magnetic field, that's B. I can change my area, that's A. What's something else that I can change? Any idea? The what? No, that would change the magnetic field. So if we change the current, yeah, so that would be number one. Think about this expression right here, this B dot dA. What else is involved in that expression? Change the time. The what? theta, right. So the other thing, this is the most common way that we use, is to change the angle. Change the time? How can you change the time? I don't know. That's interesting, right? I like that. But if you change the angle theta, then that will change the magnetic flux. So, right, that's what we do, right? In generators and the like, you crank it up, you get that gas link motor that turns the coil. That changes the respect of the angle theta of this coil with respect to this coil. So you can also change the angle. Because if you remember, this is equal to the integral of b dA cosine theta. And so if I change that angle theta, then it will change my magnetic flux. And you do this by rotating the coil. And depending upon the rate at which you rotate it, will give you the frequency at which you get electricity, or the frequency at which you get the EMF. All right, let's look at this graph. I'm going to draw it for you. Of a graph that shows B versus T. Looks like this. I'm going to break it into several parts. So this part we'll call A, this part we'll call B, this part, which goes from here to here, we'll call C, and here, this will be D, and this will be E. All right, so I have these 5 different parts on this graph, and I want you to rank in order of biggest to smallest EMF. And we'll do it as a clicker question, but I want you to go ahead and rank them. And I'm going to give you some options. I want you to tell me which has the smallest E. All right, I want you to rank them in order from biggest to smallest EMF. This is my magnetic field with respect to time. Section A right here, section B, section C right here. This is D and this is E. I want to know the biggest to the smallest, but as a clicker question, let's just tell me which. Oh, is the clicker thing been going this long? Okay, well, we'll just use it. That's okay. Where is the magnetic flux the smallest? Or I'm sorry, where is the EMF the smallest in this figure? With the magnetic field changing as shown. Where is the magnetic field the smallest? All right. We'll stop at 40 seconds, 32:40. Gosh, 32 minutes it's taking. All right, 40. Okay, let's see. So we put A, and that's right, but really it is A and C. All right, so it's not so matter what is the magnetic field, it's how much the magnetic field is changing. Like, I understand the magnetic field is lowest at this point. That's not really terribly relevant. It's really how much is the magnetic field changing. And so the magnetic field is changing the least at this point and this point. Right? Where's the magnetic field the largest? I mean, excuse me, where is the EMF the largest? At which of them? A, B, C, D, or E? You want to do it as a clicker question? All right, well, we're not using these options. We'll just use, not using these, just use A, B, C, D, or E. That is, I'm asking, where is the EMF the biggest? Which of these regions of this graph does the EMF have the largest value? All right, let's stop at 35. All right, awesome. Okay, good. B is right. It's the biggest at B, right? Because that slope of that B versus T graph is largest. We saw that before, like with position versus time graphs, that the velocity is biggest when the slope is the biggest. Same idea here. So you'll have some problems like that where you have to interpret these types of graphs and interpret what the slope is doing. All right. All right. So the biggest EMF is at B. The smallest is at A and C, and then D and E. They both have the same EMF that's going to be smaller than this EMF just because the slope is smaller. All right, so let's see. Before I do this, have y'all heard of this this new band? It's sort of an indie rock band. It's called 999 Megabytes. You heard of that band? Anybody heard of them? Yeah. You have, seriously? I'm not surprised because they don't have any gigs yet. What was I saying? Oh, biggest to smallest EMF. So our biggest is at B. The next biggest is D, but these are also equal to E. And then the next biggest to that is A. And A is equal to C because the magnetic field is not changing either at A or at C. So the biggest is at B because the slope is the biggest. D and E are equal because the slope is the same, but a smaller EMF, though notice that the EMF there will be in the opposite direction of what it was at B, but we'll still say that the magnitude of the EMF is the same. A and C are also equal because they have zero slope. Let's see, let's do a problem where we have to actually calculate the EMF. But my computer's locked up. Give it just a second. It usually takes a second. It'll catch up. Sorry, in just a moment. Y'all have the next problem on there. Can I see? Oh, yeah, solenoid. So go on to your next page. While this is thinking, I will talk you through this, and then I'll write it up on the board. So I want to know what is the EMF in the coil. I need to find out, what is the changing magnetic flux. And so I need to calculate what is the magnetic flux at one time, and then what is the magnetic flux at the next time. So it says that a solenoid has so many turns per centimeter, has a certain diameter. We put a coil inside it with another diameter of 2.1 centimeters, and then the current is decreased to 0 amps over 25 milliseconds. And so I want to know what is the the EMF in coil C. That is, I have this solenoid, which is just a coil of wire. I put another coil of wire inside of that coil of wire, and then I change the current going through the outer coil of wire. It goes from 1.5 amps down to 0 amps over a time of 25 milliseconds. Okay, looks like I got it. No, I don't. Sorry, got it. I think I can write here. Yeah, so I can still write here. Hopefully it'll come back to me. So what is my final EMF? Or what is my final flux? Now I got this solenoid. This is my solenoid. There's a certain current going through it. And then I have another coil of wire that's inside of it. So I have these two coils, one inside of the other. The outer coil, I'm changing the current. And by changing the current, I'm changing the magnetic field. By changing the magnetic field, I'm changing the magnetic flux that goes through that inner coil. And when I change the magnetic flux in that inner coil, it generates an EMF. So my final magnetic flux is going to be equal to what? Well, what's my final current? It's zero, right? So I have no magnetic flux in the final state. That when it goes down to zero current, then I have no magnetic flux generated by that solenoid, by that outer coil. So I got that. Now I need to also find out what is phi initial. And phi initial is going to be equal to B times A and we actually skipped this, so I'm going to step back for just a moment for a solenoid. So a little mini lesson here on a solenoid. I think this is on your equation sheet. But for a solenoid, it's a switch right here, that if I have a current going through it I have N turns of wire, or excuse me, not N turns of wire, but N being the number of turns per unit length, little n. Because that's usually how we define solenoids, not by the number of turns, but say the number of turns per centimeter or whatever. Then my magnetic field that's generated by that solenoid is equal to mu naught, that's a constant, times the current, times N. This is similar to what we've done before, and it's largely just over geometrical argument, but we're not going to get into it. It has to do with Ampere's law, if you're familiar with that. But anyway, for a solenoid, the magnetic field is given by this. So now I want to know what is my initial flux. So my magnetic field of that solenoid is mu naught I times N times the area. That's the cross-sectional area of that. And that's equal to 4 pi times 10 to the minus 7 times my current, which is 1.5 amps, times N. Now N is given in the problem, I think it was 220 turns per centimeter. Need to convert that into SI units, so it actually turns out to be 22,000 turns per meter. That's if I'm looking at a solenoid. Let's say this is 1 meter length, then that would mean that there are 22,000 turns of wire in that 1 meter length. It gives the linear density of those turns. So 22,000 turns per meter, and then we also need to know the area. Is the area given? No, but it gives the diameter of the coil. So I just use that to calculate the area. Turns out that that is 3.464 times 10 to the minus 4 square meters. This is just the area. The area is equal to pi r squared. So I take half the diameter, square it, and multiply times pi. All right, so that gives me the initial flux. And the initial flux then works out to be 1.44 times 10 to the minus 5 Webers. This is theta initial. So I got my final, and I have my initial. Now I want to find my change in flux. Let's see if I can get back to my page here yet. No, I'll just do it here. I'm gonna go over here to the side. Sorry guys, I don't know where my next page. It's there. It's just not letting me get to it. So now I want to calculate my change in flux. That's d phi dt, and that's equal to, well, phi final minus phi initial divided by delta t. That's what dt is. It's just an increment of time. And so this is 0 minus 1.44 times 10 to the minus 5. That's all in Webers, divided by 25 milliseconds, which is 25 times 10 to the minus 3 seconds. And that gives me a changing magnetic flux, or a rate of change of magnetic flux, equal to 5.76 times 10 to the minus 4, minus actually 5.76 times 10 to the minus 4. Now, let me step back through what we did here. So we have this coil within a coil. The blue coil has a current that changes. That goes from a current of 1.5 amps down to a current of 0 amps in a certain amount of time, in 25 milliseconds. So I calculate my magnetic flux in the final state. There's 0 current, so there's 0 Webers of magnetic flux. And then I do it for the initial point. That is, what is my magnetic field times my area? This magnetic field of a solenoid is given by this expression. We didn't do this last chapter, I skipped over it, but it's in your equation sheet. The magnetic field of a solenoid. And that magnetic field here, mu naught I, this is the number, the linear density of the turns, in turns per meter, times the area. And then once I get the area here, I can calculate the initial magnetic flux. Then I want to know the EMF, which is d phi dt. So just do final minus initial over our time, and I get this value. This is measured in volts, so it's not the final answer, because my EMF is actually equal to N. I'll do it down here. This is the final step. The EMF is equal to minus N times d phi dt. And so I multiply the number of turns Oh, did I have N in your problem? Did I have 130 turns? No. So let's, yeah, that's for a different one. That's for the outer coil. So on the inner coil, I have 130 turns. So here, on the inner coil, I have 130 turns of wire. It's not terribly important, but if you have multiple turns, then it increases your EMF. All right, so that's my value for N. Keep that separate from the little n, which is for the solenoid, the outer coil. So then this is minus 130, that's N, times this minus 5.76 times 10 to the minus 4, giving us a final voltage of 7.5 times 10 to the minus 2 volts. So that's our final answer. What I did is I calculated the initial flux and the final flux divided by time in order to get d phi dt, and then negate it because the EMF is negative d phi dt times N, which is the number of turns. There's a homework problem that's similar to this, probably a similar one on your test too, something similar, where you have to step through and figure out what is the induced EMF in this. All right, we'll stop there, guys. We'll do some more of this. If you didn't get it today, that's okay. We'll get it later. But I would start looking at your homework, okay?